started to ask the question how one can get from very simple interactions in which the elements don't have any particular properties of adaptation or intelligence. How can one get a behavior in which the emergent collective objects do have a behavior which at least it's a model metaphor for the kind of behavior we see in real life when it comes to living organisms. So we wanted to bridge between two behaviors which are in a sense irreducible, because this one is has a causality from past to the present and to the future, while this one sometimes looks as if it is the causality comes from the future because they want to live, they want to survive. And in fact, we will see that the systems which we get, they survive much beyond what the naive behavior of their composing elements would suggest. So our guide in this is this slogan, "More is different," which Phil Anderson coined quite a number of years ago, and I explained it in the past. And he also made more specific by saying that the real world is controlled by the exceptional, not the mean, by the catastrophe, not the steady drip. So much of the traditional tools of the exact sciences, physics, for instance, in which, at least at the beginning, it was the averages, the statistical averages, which were considered as being important for understanding the system. We'll see that it is actually the least probable events which are actually driving the behavior of the system. This puts some problems on applying these methods to social and human sciences, because on one hand we want to be able to make very specific quantitative predictions, which in principle can be confronted with the reality and corrected or raised to the level of a theory which is at least partially and temporarily proved. On the other hand, we need a kind of oversimplification if we want to be able to be precise about what we are speaking. And this, we have found that this can be realized by concentrating on what are the particular mechanisms which are ensuring this amplification of microscopic properties and microscopic events of the elementary components of the system. What does it make this amplification to the level of systemic changes, of very dramatic changes in the entire system? And we found that we have a series of effects which are self-enhancing themselves. We call them sometimes autocatalytic. We spoke a little bit in the past about it. We speak more and more about it. And then this kind of ideas did appear in the past in many instances. But it was difficult sometimes for people to accept them, because it wasn't clear why should one have this kind of self-sustaining mechanisms in existence. And the answer is that if they are not in existence, then we don't see at the macroscopic level anything. So when we see at the level of macroscopic phenomena something, in spite of the fact that the entire system and the entire dynamics is defined at the level of the microscopic elements, if we see such a thing, then for sure it has to be some mechanism which is amplifying it. An example would be that when we are in this room, there is no autocatalytic process about the behavior of the molecules, and therefore we are not very much aware of the fact that the air is made out of molecules. On the other hand, if you look at the stock market, then you see that in spite of the fact that it's made out of many millions of people too, there are fluctuations which are very macroscopic, and they are sometimes produced by some simple events, like somebody pushing the wrong button and bidding 100 million, 10 billions instead of 100 millions in the market, as it in fact happened in 2002 in Lifey stock in London. But in these systems in which there is this kind of self-amplification of the processes, like in this case of the stock markets, we do have macroscopic phenomena happening, and then we are aware of the fact that the system is made out of many microscopic elements. So we introduced in the last lecture the simplest system which can produce and can explain this kind of jump from blindly behaving entities like these A's and B's and between the collective object which appears spontaneously in the system, in this case islands or herds of bees, which we have seen that they have adaptive behavior, and I will make this point even more detailed in this lecture, because it seemed that in the previous lecture I was a little bit going too fast, so I want to be now much more explicit. So in a sense, this lecture is repeating in a different way some of the ideas which we already introduced before. So we had these elements A and B, and they were living in some space which we figured by a lattice, but it doesn't have to be a lattice, and definitely not a regular one. And there are very, very many interpretations to such a system. One of them is that you can imagine that the sides on the lattice are different sectors in the economy, and the connections between them is, let's say, the payments between one sector and another. And the B would be the capital which goes between those places, and A would be different elements which are good for the capital to proliferate. In particular, when we calibrated the model on the detailed data which we had about Poland after the liberalization, we have found that the dominant factor A for the A's was the education of the people in that location. So many times this model has been represented a little bit exaggerating in terms of angels and humans, but basically the point is that whenever on the same side you have A's and B's, then each pair of A and B's can create another B with a certain probability, which we'll discuss now. And there is also the probability that the B's can die. The A's cannot die and are not born in this simplest model. They are just going around randomly. So we had this little representation of how the A's can go around and how the B's can go around, and how when the A's and the B's are not on the same side, nothing happens, but when they are on the same side, there are some additional B's which can be generated. And the number of B's is proportional to the number of pairs A and B which can be created, which means with the product between the number of A's and the number of B's existing on that side. That is the rule of the game. and the bees can die, as you say. And we also mentioned that the bees can compete or fight between themselves, such that there is some probability that some of them will die if there are too many of them. But we will not discuss in great detail the aspects of it. We introduced it just to make sure that the number of bees would not go to absurd values. As I said, there are very many interpretations of this AB model. One of them is to imagine it's a very simplified model of how you can represent the appearance of life in on Earth. You can imagine that A's are proteins and the B's are the DNA. So the B's can multiply themselves, but with the condition that they have the prime material for indeed multiplying themselves. Let me close the door. Another way to think about the system is to think about the sites, not as real sites in the real space, but as representing each site representing the genome of one of the animals, and the animals or the individuals being B. So when B is on a certain site, then it has a certain DNA, a certain genome. And jumping between sites means mutations in the genome of B. And A is a kind of parametrization which parameterizes what is called in this kind of models the fitness landscape, which means if there are many A's in some location, it means that this is a very fit genome. Carriers of this genome will multiply faster, which is exactly what the AB model is saying. And there is also the immune system functions on the same principles, but I will not discuss it in detail. I want now to return to some part of the explanations of last time, which maybe were not completely understood. So now I'm zooming in on one of the squares, or if you want, I'm considering naively, meantime, that the entire lattice would be just one single cell. And then according to the rules which I said, for each pair A and B which can be created, I will have another being possible to be created, but with a probability lambda, which means and doesn't have to be 1. So essentially, if lambda is 1/3, it means the following. For each A, each of the B's can create another B, but with probability 1/3. So what does it mean? That for the first A, together with these 3 B's, in principle, it could create 3 B's, but with probability 1/3. So the expected number of B's which will appear out of the first A and all the B's will be 1. And the expected outcome of the second A with the initially 3 B's would be 1/3 times 3 B's, the other 3 B's. So in the end, what I will have as the expected outcome after one time step, so I imagine that this happens at some time. I call it time t. By t, I mean it's just a symbolic way to say that it's today. And then t plus 1 would be tomorrow. So if at time t I have this kind of situation in which in the system or in one of the cells I have 5 A's and 3 B's, and if the proliferation rate per pair is lambda equal 1/3, then I will have a situation in which I have 5 B's being created in 1 unit time, let's say tomorrow. Or it could be, depend on the organism. If it is microbes, it will be in 1 minute. If it is people, it would be in 1 year or so. But the main point is that the rule of the game, as we defined it, and it's in a sense not a proof. It's a definition of what we say that it happens, is that the number of new b's which appear, which in our case was 5, it's equal to the number of b's which existed before, 3, at the time t, times 5, the number of a's which existed, which are placed there, and times 1/3, which is the proliferation rate. So symbolically speaking, if I call 1/3 lambda, and if I call the number of a's in my system or in my cell, whatever I speak about, little a of t, and this and the number of b's little b of t's, then the number of b's in the next time step will be the number of b's at time t plus this quantity. Of course, I can put the b on the other member and say that b at t plus 1 is equal to b of t plus lambda a of t b of t. These are the rules of our game. So sometimes we'll use another notation to make the point that the a and little b might depend on the particular site. Sometimes we can call it mb, which is the number of b's, and this rule of evolution of the system from one time to another, from one time step to another time step, is that the number of b's goes to whatever I had before, plus lambda times the number of a's times the number of b's which I had before. So in general, if I have a certain number of b's in a system, like in our case it was 3, then after one time step you get what you had before, plus times 1, which means that I have what I had before, plus lambda na, which is the factor by which I extract how many new b's are appearing. So this is how we get to this formula, which is very important from now on, that the value of the number of b's in a system or in the cell, depending on what I'm discussing, at one step forward, it's equal with whatever there was before in that system times this quantity, which is 1 plus lambda a of t. Of course, by discussing this, I didn't discuss the death of the b's, but this is much simpler because essentially it's just saying that, putting minus mu and saying that essentially part of the b's which existed before, they are dying because of the death. The more complicated thing was to explain this dependence on A and explain that our rule from the beginning was that the change in the number of b's is proportional to the product between the numbers of A and the numbers of B in the system times lambda, which is, so to speak, the proliferation rate per AB couple. So I'm going to give now a lot of examples of how to do that, even if you see this kind of symbolic way of expressing it, maybe it's not familiar to some of you. I give now examples which show how we proceed, what is going on. So in a sense, it's an operational definition of the mathematical definition, paralleling the mathematical definition which I made before. So I'm saying if today, or at the beginning of time, there were 6 b's in the system, and if there was 1 a and if the density of a's was 1, which means that on each of the locations in the lattice, this time I'm taking a lattice which is just, it's again regular, but it's one-dimensional rather than two-dimensional. So you can imagine that there is one-dimensional world and there are a's around. When I start with my process, I put 1 a in each place, which is a realization of the fact that the average number of a's per site is 1. Therefore, I put 1 in each place. Of course, because the a's are moving, you will see that they will not stay exactly like this. Sometimes there will be 1 a jumping here, and then it will be 0 left here and 2 here, and we'll see that this is going to be important. But we start now with a naive assumption that if I have 1 a per cell, then I really have 1 in average. Then I really have 1 a per cell in each of the cells. And I'm taking lambda equal 5/6, and I'm taking the death rate equal to 1. Note that according to our rules, which we expressed in the previous lectures and kind of reminded to us again, if you multiply a times lambda, you get 5/6, which is less than the death rate. So we do expect that the number of bees will decrease. But this is exactly what I'm showing in more detail on this slide. So the births in each cell would be the numbers of bees in each cell, which is 6. You see, there are 6 in each cell. Again, it's an oversimplification, and it's not I'm not trying to defend this oversimplification. Quite contrary, what I'm going to show to you that assuming that the number of a's in each cell is equal to the average of the numbers of a in general, that is an assumption which is very misleading and in fact leads to the wrong results. But we are playing this game for the moment. That you have 6 b's in each side, you have 1 a in each side, and you have lambda 5/6, and therefore it is 6 times 1 times 5/6. The number of new bees being born on each side would be 5 in this case. Now, the death would be terrible, because I'm putting that essentially in 1 unit time, all the old guys are dying. There are, of course, animals which do that, like octopuses. They die after giving birth to their small ones. But this is not to be worried about, because the number of little ones are millions, so which very small number survives. So the fact that the last generation dies is not so bad. So essentially, it's minus the number of deaths will give a contribution to the number of bees on each side, which is minus b times mu, which is minus 6. B was 6 times 1, it's minus 6. So all the old ones are. So I'm living after 1 step in time. So if I was at time t, a time t plus, if a time t or a time t equals 0, I had 6 bees per side. Now I'm having only 5 bees per side, and if I go on, it will be less and less until eventually they will die. This is the prediction if I make this assumption that if the average is 1, the average of number of a's per site is 1, then the number of a's on each site is 1. But so then I get this formula that b at the next time step, it's b at the previous time step plus the birth minus the death, which is 6, which were plus 5 minus 6, it's equal to 5. But now I'm going to do exactly what I told you before, that the a's can move. And in particular, they suppose that they make this move, that 2 of the a's moved on their neighboring sides. So now I have 0 a's here, 2 a's here, 0 a's here, and 2 a's here. And I want to see what happened if this happens. You naively speaking, you will say, well, they are the same a's, they are the same bees. How this can be so different? So I'm going to show that it's going to be very different, and this is very simplified explanation, which has some of the crucial elements in the mathematical proofs which prove that these systems, even when they look like leading to the decay of the number of bees, in fact, they lead to the increase of the number of bees. But not only that, you will see they also lead, the way the bees are surviving is by forming collective objects which are behaving adaptively, and even they look as if they are intentionally trying to stay alive. You will see that. But meantime, we are back to this kind of very, very simple arithmetics. I definitely wouldn't call it mathematics. And even that arithmetics is done in this kind of little cartoons, which do not involve significant computations. So now I have 2 A's on some of the sides and 0 on the other, and I'm repeating the computation which I did before. The number of birds on each cell would be the number of B's on each cell times the numbers of A on each cell, on that particular cell, times lambda. Except that now A sometimes is 2 and sometimes is 0. And because of this, I make the computation like this. I say B is 6 times either 2 or 0, because I want to compute in parallel what is going in both these sides, and times 5 over 6. Now, obviously, if this is 0, then it gets 0. If this is 2, then it's 6 times 2 times 5 over 6, which is 2 times 5, which is 10. So in the places where I have 2 A's, I will have another 10 B's being born, which might look large to you if you think in birth rates of people, but as I told you, it's very small if you think in terms of octopuses. The death rate, we know that it's 1, and therefore the number of deaths on each site is minus, I put minus because these are deaths, they are subtracting from the number of B's. It's 6, and this is 1, so it's minus 6. All the old generation is dying, which, as I told you, it is not so unrealistic for some of the species. So what happens, you see, what happens here is that on some sites, the entire bee population has disappeared. But on this side, it has increased very significantly. Now, if I apply again the one more time step, so yeah, I started, let's say, a time equals 0 with the bees being 6 over the entire, in each of the cells. Now, if at time 1, the one step after that, I'm having 10 guys here and 0 here. Now, the guys which are 0 here, they will stay 0 for 2 reasons. If the A's are not moving in the meantime, then I have 0 A's, so definitely they will not multiply. And on top of this, even if they would try to multiply, since there are none of them, then there is nobody to multiply. So these cells will remain empty if there are no A's intervening in the meantime. On the other hand, these ones will continue to grow with the same rate. And it will get even more than 10, so they will continue to grow. So, so here is another example. This time I'm taking lambda equal 1 over 3, mu equal half. And now I'm having 6 times 1 times 1 over 3. It's equal to 2. These are the number of births, you see, in each side. And the number of deaths, it's 6 times half minus 3. So 3 of the guys in each cell are dying. And therefore, on each cell, I will have 6 plus 2 from the birth and minus 3 from the death. It's equal to 5. Another way to look at this is to say, OK, so what are the births and the deaths? Let me be more explicit. So B, the next time step, is equal to B original, let's say B today. If t equals 0 is today, it could be yesterday, and then t equal 1 would be today. So it's what I had before, plus what I had before times A times lambda, which this was the birth, and we have many times written this thing as birth. And this is the death. I omitted here, it's a mistake. It should be minus B times mu. So, which is correct here. So it's not minus 6, it's minus 6 times 1 over 2. So I have 6, it's a B. 6 times 1 times 1 over 3, it's B times A times lambda. And minus 6 times 1 over 2, it's the death. Now, I would like to write it in the following way. You see, each of the terms in this equation in which I'm deducing the value of the b at t plus 1 as a function of t at 0, they are proportional to b at t equals 0. So I can take this b outside and write that b at the next time step t equal 1, it's equal to this times this entire bracket. Okay? So when instead of writing b times 1, b times a lambda minus b times mu, I'm writing b times 1 plus a lambda minus mu, which in our case it's 1 plus 1/3 minus 1/2, and it gives b times 5/6. This is 5/6. So b is going down. B at t plus 1 is equal to b at 0, at t equals 0, times 5/6. It's going down, which is indeed the case. I started with 6 b's, and now I have only 5 in each side. But you should remember this formula, because it's going to be important. Because what happens? Suppose that now I go at t plus 2. I make one more step in time. Then I will get another factor. Then it will be that I get another factor of 1 plus a lambda minus mu. So essentially, going at arbitrary time t, 1, 2, 3, 4, I'm getting what I had at the beginning times this bracket, the power 1, 2, 3, 4, and so on. If this bracket is larger than 1, then I will have larger and larger values of b. If it is smaller than 1, as it is the case in this, in our case, then I will have smaller and smaller. Then now I begin with 6, now I have 5, and eventually I will get 4, 3, 2, 1, and nothing. So this is the kind of reasoning we are going to do about what happens in time with the systems or with the particular cells. And again, I can play this game with the same parameters. What happens if the A's are moving, and if I have situations in which the average A stays the same? So if I look at the entire system as a cell, nothing has changed. So this is the point. In the past, these equations, which were, as I said in the previous lecture, they were essentially, this kind of system was invented more than 200 years ago by Malthus, and then developed further into what was called the logistic equation. But the assumption was that each of the cells are, they even didn't speak about each of the cells. They were thinking that the entire country, let's say the Netherlands, is one cell, and they applied the formula for one cell, and they got the result. A certain result. And now I'm showing that if you take into account that the non-uniformities in the system, which are arising from just the fact that things are moving randomly, you don't have to assume that there is an invisible hand which arranges the things specially. Just letting things happening randomly, you have this kind of situations in which in some places there are no A's, and in some places there are larger number of A's, and the results are changing very dramatically. In this case, I have 6, again, a number of b's. This again, A can be 2 or 0. Lambda can be 1 or 3. So I have either 0 or 6 times 2 times 1 over 3 is 4. And the death is minus 6 times half. It's minus 3. So in total, I have either an increase, either 6 plus 1 or 6 minus 3, according to whether I'm on this side or on that side. And indeed, you see there are the 4 guys appearing here, and there is also the 3 disappearing. And again, I'm showing that you can express the same thing, not only in terms of saying that b at the next time step is b at the present time steps times plus b at the present time steps times a times lambda minus b at the present time step times mu. But say taking the present b outside this and seeing that in fact the basic thing which happens is multiplying the present population by a certain factor. And if this factor is larger than 1, as it is in this case, you see, in this bracket I have it's 1 from here. A is either 2 or 0. So it is a lambda is 2 over 3 or 0. So it's 1 plus 2 over 3 or 0 minus half, which means that it's the population in a certain system, in a certain cell, at the next time step, it's the population at the present time steps times either 7 over 6, which is larger than 1. So if I go on, I get larger and larger values, or 1 over 2, because it's 1 plus 0 minus 1 over 2, and which means that it's going down all the time. So this is a little movie about this. So I'm taking now again a similar situation. I take lambda equal 1, mu equal half, and a equal, let's say, 2 over 14. Why do I take it 2 over 14? Because I have a lattice which is 14, and essentially I have 2 a's. But if I don't think in terms of having 2 a's independently on two sides, but I'm saying, well, there is an average of 2 over 14. I'm dividing the a's and assuming that they are uniformly spread, this white thin spread here. And these are the level of the b's, the blue thick spread here. So, so naively speaking, if I think about the entire system as one cell, then what happens in that cell, according to this rule, is that I have 2 over 14 times times 1 minus half, and I have a decaying in time. I will have 1 minus 5 over 14. The 1 plus a lambda minus mu would be 1 minus 5 over 14, because mu is larger than a plus lambda, so this is negative, and this is less than 1. And if I multiply a number with itself again and again for each time step with itself, then I get smaller and smaller values. However, in reality, what happens, it's very different. If I take into account that the a's are discrete, are either there or not there, then I don't have 2 over 14 in each of the cells. I have either zeros in 12 of the cells, or 1a in 2 of the cells. In the cells in which I have an a, the relation, what happens to the b, if I have a certain moment, let's say at the beginning or even after I computed what is in the next time t, I can compute what happens yet in the next time. Then I will have what I had in the previous time times 1 plus a lambda minus mu. A is 1. So it's 1 plus lambda minus mu. And since lambda, what was it? Lambda was 1 and mu was half, then I have essentially it's 1 plus half. So I get a factor of 3 over 2 here. It's a large factor, definitely larger than 1. While here, where I don't, in all these other points where I don't have an a, it's just 1 times plus 0, because there are no a's, minus half, which is half. So what happens in the first time step? After I began with a uniform B population, but now after I applied once this multiplication, this birth and death of the bees, what happens is that because at the point where I have A's, there are births, then even after I subtract the death, I'm left with a factor 3 over 2. So the height of the number of bees here increased by a factor 3 over 2, while in all the other points, it decreases by a factor of 1 over 2. So now, since there are 12 12 places where it went down, and only 2 places where it went up. In average, the entire population went down, and in fact went down very much similar with what the naive assumption would tell us. So somebody which would have made this computation assuming that this is just one single cell with a density of A, with a total number of A equal 2, but spread uniformly throughout the lattice, and therefore would get that the bee population is going down, he will say, oh, I was right. The fact that you bothered to compute separately the places where there are A's and the places where there are no A's, you just got upon yourself more headaches. I computed just assuming that the A's were, the 2 A's were distributed uniformly in 1/7 A for each side, and I got more or less the same result. And the same thing would happen the next time. The next time I had after the first step I have 3/2 times the initial value of the bees. Now I have 3/2 and again a 3/2. So it's 3/2 squared, and here I have 1/2 squared. It went down by half, and now it went down by half again. And again, since there are so many which went down and so many which went up, again, the person which would take the average would think, okay, I was right. But what happened at some stage is the following. The ones which are going down don't matter anymore, because first they went down by half. And it was exactly by how much the other 2 went up, by half. So there were 12 going down by half, and 2 going up by half, and they were half of the same quantity. Therefore, the ones which went down were in a very strong majority. But now the ones which are in majority are still in majority in number, but they are so small already because they were divided by 2 twice that the next time that I'm dividing them by 2, in any case, they are not so important. Most of the population of bees are here, where I have 3/2 to a larger power. So what really now drives the system, as I in fact promised before, is not the average, but the very singular points in which I have A's. In this case, there are 2 points. So the actual system starts separating from the naive system, which takes the average over the entire system, and it starts increasing. And as time goes on, these ones are really going to 0, and these ones are really dominating completely, and they have an exponential increase. It's just 3/2 to the power t, where t is the number of steps by which took place, and each of the steps multiplied the number of bees on that side. By a factor of 3/2. So this is what you are going. And as you remember, and as I will show you again, this is exactly the behavior which we found in the case of Poland after liberalization, but we found in many other countries. There are 40 different countries, and there are many other details which are going to check. For instance, we are going to check that this double exponential or crossing exponential behavior, in which there is one exponential going down, which at the beginning is dominating, and then there is another exponential going up, which becomes dominating after they are crossing. This behavior is very generic, and we'll find it in many applications in different systems. But in the meantime, we just go on with this. And then the point is the following. Of course, I took the situation in which the A's were staying after they moved, after they jumped first, and they introduced this inequality between the different cells. Some cells were left with 0 A's, and some of them were left with 2 A's. Then we got indeed this result, which is definitely completely out of the predictions of the naive system which takes the average over the entire system. But now the question arises, yes, but the A's are not jumping only once, they are jumping all the time. So maybe by these guys which are going up at some stage when A jumps from there, they will start going down. So maybe if the A's are going fast enough away from these islands which they are creating, maybe the entire effect will go away. Now, in order to prove that the effect does not go away, and especially in 1 and 2 dimensions, it doesn't go away at all, and as I explained last time, the result is very astonishing, that if the system is large enough, then no matter how small is the proliferation rate lambda, no matter how large is the death rate mu, no matter how small is the density of A's, the B population always increases on such a lattice. Of course, increases in very singular points, not uniformly, but that's another point. So now, so these theorems, I'm of course not going to prove them in this class, but I'm going to give some explanation of how comes that even if the A's are moving, the B population is not decaying. So I take a very extreme case in which the density of A is 1 over 14 now. There is only one A. So when I start with all the B's uniform, in all the rest of the system, the number of B's is going down, except that where A is sitting, where the B's are going up. On top of this, the B's, you remember, they are jumping. So some of the B's which are created at the A location, they are going to increase a little bit, or at least not allowing to decrease the population of B's in the neighboring cells. So as long as A is sitting there, one has this growth of a herd of B's or an island of B's, which is essentially completely dominating the B population. And if A would stay there forever, then it will go exponentially. But A can jump. What happens when A jumps? You see it jumped. So now all these guys which were at this position, now they don't have an A here. They are going to go down exponentially, like with the parameters which we last used. When mu was half, this will go, each time step will go down by a factor of half. While here it will increase according to the parameters which we discussed by a factor of 3 over 2. So I'm taking a picture of what was the height of what was the profile of the B population at different sites at the moment that A jumped from one place to another, because I want to compare with what happens after the jump of A. After the jump of A, as I said, this column, this site, in this side the B's are increasing, in this side the B's are decreasing. Also they are decreasing here because they are not getting any more diffusion from this side, because it doesn't have it for itself anymore. So at some stage what happens is, of course, if A is here, then it also diffuses here, and it gives a little bit here, but less than what this one goes down. And eventually, what happens is that if A stays enough here, you see what happens. There is a crossing. This, the dominant process until this moment was that the highest island was going down. But because it's going down, it becomes, and this one was going up. And because of this, at some stage, this is not anymore the highest island, and this is the highest island. So now it's again the situation that the highest island is actually going up. So the system is increasing. And if A keeps going, the island 2 will keep going after the A and increasing. So this is, in a nutshell, in a very, if you want, naive and simplifying way, the way in which you have, just with one single A is enough, but of course with more A's it's much more realistic, that the herd of B, the island of B, which is formed around an A, is following the A and increasing. And I'm emphasizing again, the one which is following the A are not the individual B's. The individual B's are just going randomly to the left and to the right. They don't follow the A's. It just happens so that in the place where there is no A, they will die, and in the place where there is A, they will grow. And because of this, it looks as if the B's as a collective, they are forming an object which is searching for where A is, following it, exploiting it, and realizing a situation in which the bee population is surviving in spite of the fact that the naive computation based on taking averages or taking the entire system as a whole would predict that, that they are doomed to death. That is the main point. And as I said, this kind of mechanism is true for any parameters in 1 and 2 dimensions. And now you can say, but what happens if the A's are going very fast? That's exactly where the 1 dimension and 2 dimensions are entering. If A is going very fast, there is a probability, there is half of the probability that it will go away from the previous islands, but there is half of the probability that it will actually return to places where it was already, and where there is already a population of bees which is dying, and only praying that A will be there and will save them and will make them grow again. And because of this, of course, again, you can think about the island that is praying, because the individual bees don't care. The individual bees' death rate does not depend on whether an A is there or not. It's only the birth of the next generation which depends on the A. So even this praying, it's a collective property, if you want, or this behavior which looks like an adaptive behavior. It's a behavior of the islands and not of the individual bees. So this is the thing which I was promising, that this very, very simple model, it's a metaphor about the paradox which stands behind the emergence of adaptive systems and of life in particular. Because we look at ourselves and we say we are very adaptive, we want to live, we do actively do things in order to live. And on the other hand, we are made of atoms which they couldn't care less about anything. They just don't even know what is going on. And in our own case, we don't know yet. It's a lot of chemistry and a lot of other things which are not yet understood at all in detail. But this system, we invented it, so we know very well that the basic laws, it doesn't try to survive, it doesn't try to adapt, it doesn't try anything. But it is only these islands which are and this collective objects which are appearing, which start having a behavior which definitely could be defined as self-serving, and in fact very successful at it, because it succeeds to make themselves survive even in conditions in which, as we computed, if there weren't bee islands, then the bees would die if everything would be uniform. So there is a kind of circular argument, which is pleasant again, because it's a logical circularity which is built on a very precise, I wouldn't call mathematical, arithmetic mechanism in which these objects are emerging and are surviving. This is actually a simulation which gives you more details about what is going on and will help us to make contact with what happens with systems in reality, especially economic systems. So what do we see here? the space is one-dimensional as it was, but except that instead of taking it horizontal as we took it before, we imagine it in having this position, still horizontal but inside the figure, because I want to take the other axis to be the time, the evolution of the system. So this graph is just the evolution of the previous system, except that now I'm taking slices of time which are like this, and the space is like this. And the A, this single A which I was taking, it's someplace here. So at the beginning, everybody, I take the height of the B is constant. So what happens, we have seen. In all the places where, except the place where A is, everybody goes down. You see this line is not parallel to this line, it goes down. So the B population at all the sites which are not close to A, it goes down. At the one which is close to A, it goes up, of course. Sorry. It goes up. And from time to time it goes down because the A jumps. And you remember there is this catastrophe. The entire column which A lived is going down. This is a logarithmic scale. So these little jumps here are actually enormous jumps by a factor of 5 maybe. So the population is going down. But overall, it's actually going up. And moreover, it's filling the entire system. So we have this prediction that at the beginning, some places in the system go up and some go down. But towards the end, everybody goes up because this island has essentially filled the entire system. So this is going to be important, and you will see that it's fulfilled by the data, empirical data in various economic systems. So this is a few A's which are going around, and these are the islands which are following them. And you have also seen that the height of the, not only the position of the island is changing and it's leaving a trace of dying bees behind them, but also the height is going up and down according to the fact that each jump in A produces a decay in the island. So how do we interpret it? You see, it's already in general when I speak to my colleagues in exact sciences. This kind of interpretations of the system are not emphasized, but I would like to emphasize them in front of you because some of you are interested in subjects like this, in origins of life or in the origin of species, and especially in the way we are thinking about it. So if you think about the way we were interpreting in terms of the origins of life, we were thinking about the A's being proteins, which are, let's say, existed in the primordial ocean. And the B's were the self-reproducing agents, maybe RNA, maybe DNA. And then how do we interpret in this context the fact that the AB model, this model with A's and B's, instead of letting the RNA to die, even if it has a very low rate of reproduction, even if it is very unstable and it decays with rate mu, very large rate mu, and then even if the number of proteins are not very, the density of protein is not very high, if the system is large enough, then you will always have some region in which singular fluctuation would produce the right herd of bees, the right island of bee. And what would be this island? This island, if you think, it is essentially a protocell. This kind of very limited space in which, as opposed to the entire environment, which is still deprived of the bees, in that particular place, there are a lot of bees, and not only that there are a lot of bees, they are doing everything. The island itself is doing everything in order to detect and exploit the fluctuations in the A positions. So in this respect, this model is telling us, well, do you know what the cells are doing? The cells are essentially the trick of life to make sure that in spite of the fact that in average it lives in an unlivable and extremely unhospitable medium, still it will survive. And a similar effect you can discuss in terms of species, because if you think in terms of the genomic space, as I mentioned, in which each site corresponds to a certain genome, and each bee is one individual, and if it lives on a certain site, it means it has that genome, and the A's are labeling what is the situation of that genome at that particular moment, whether it's advantage niche with a large fitness or not. Then what the AB model says about it, it says, well, in most of the space, the bees are in really bad shape and they are dying. But there is a certain, there are certain regions, separated regions in the genomic space, which are in fact capable of keeping alive, even if the conditions are changing, and therefore not always the same genome is advantaged because the A's are going around, and therefore the fitness of each genome is changing. And even because in spite of this, you have this kind of separated patches in the genomic space in which the bee herds are surviving. So again, if in this island are essentially species. They are groups of genomes which can be obtained easily one from the other by single mutations, and which collectively are able to keep alive in spite of the fact that in most of the genomic space one has very unlivable organisms. So the species are again, like the cells, some trick of life to survive in a medium and in conditions which are, in average speaking, unlivable and very unhospitable. And the same thing is about the immune system, but I wanted to make a digression. Let me see if I have this digression. This file is finished. I will go to the next one. But before that, maybe I make one more comment about this Darwinian. Sorry. Let me make a comment about this issue of speciation. You see, the way the species are surviving is an illustration of the Darwin idea, because essentially it says the bees are born with some mutations, because the bees can jump from one side to another, and the ones which are landing on a site with very few A's, which means very low efficiency, very low fitness, they will disappear. And the ones which are jumping on a good fitness site, they will survive. So this is the Darwin mechanism. This Darwin mechanism for surviving, it's actually not very efficient. You have to go a few generations. If you have significant changes in the A's, significant changes in the environment, then it takes some generations for the species to adapt to that. But if you return to the interpretation of the real space, then there is another effect which is not sufficiently emphasized by people thinking about selection, in which actually what happens is that even stupid organisms are actually, instead of the medium selecting the organisms are selecting the medium. Now, I'm not speaking about humans which are saying, it's not good to live in the unindustrialized place. Let me move in another place. This is a conscious decision. But I'm speaking about, let's say, completely stupid organism. Suppose that the rabbits would be terribly stupid, that they are just moving randomly, not looking for anything. Still, according to the kind of analysis which we had in terms of the AB model, the new rabbits, lo and behold, are always born in places where it's good for rabbits to be born. Of course, it's trivial, because if these places weren't good for rabbits to be born, their parents would be there. The bees wouldn't be there to give rise to the new one. So you have a selection of the medium by the species, not because the species is intelligent, but because this is an intrinsic property of this kind of emergent systems. And it's not only true for rabbits, but it's also good for the capital, because in principle people still think, though my former student Moshe Levi, which is a professor here, he had a paper, are rich people more intelligent? And he made some statistics, and he put this under a great question mark. So this model is saying, look, even if the capital B is completely randomly redistributed, as long as it's redistributed in approximately in the same places where it was generated, then automatically there will be this island which are following the technological or market development, and will make the economic life going on and succeeding, even if in average you would swear that this thing cannot work and the entire economy must disappear, in the same way in which our initial analysis of the AB model was swearing that the bee population has to disappear. So this is a kind of mechanisms which this very simple model is teaching us, and we were always very happy with this model. You know, in the place I'm coming from, there are some fields in science in which model is supposed just to express in a precise way some theory which you have about what happens. So whatever you put there, it's what you already know, and it only proves that you are right. What we like in where I come from is that what you put in is not what it comes out. It comes out something completely unexpected, and in this sense the best models are the model which, as I say, they are more intelligent than their inventors. And I think that the AB model is such a thing. Let me go to another file. These files are extremely large, so I had to split them. Okay, so let me see what I have here. Okay, so let's see. I'm going to discuss a little bit about this logistic equation, which until now I neglected. Okay, so slideshow. So in the in the previous set of slides, we had this by now very well known to us mechanism by which if we have a certain number of A's on a site and a certain number of B's, then you get back the number of A's and the B's which were before, but you also get this kind of n times m, the multiplication of both of them, which when you use these notations, it's b plus lambda a, and it allows, and I was neglecting here in this notation the death rate, but I also was neglecting something which, especially last time, people kept asking me about the additional term, the saturation term. So maybe now we'll speak a little bit more about it. I hope that you understood already this thing, which is saying that if I start with a certain bee population at a certain place, and if I can, if it is a cell or the entire system, of course, with the entire system we have these problems of non-uniformity, then at time zero I start with b. At time 1 I have to multiply by what it was before, 1, which is b itself, plus the birth rate minus the death rate, and after 2 time steps I have yet another multiplication by the same factor, and so on. So in the end, the behavior of the number of bees in time is an exponential behavior, and the exponential can be if this quantity is larger than 0, then the 1 plus this quantity is larger than 1. And then when you raise it to larger and larger powers, it gets increasingly large. And this is called an exponential increase. On the other hand, if lambda a is less than mu, then 1 plus lambda a minus mu is less than 1. And then multiplying with itself many times, it only makes less and less population. So this is what Malthus have found. As you see, he didn't think in terms of what happens if you have some inhomogeneity in the system. And as I said, if at the beginning, if you start such a process, then the only thing which is important is this term. But as b goes larger, now if the exponential is going down, then this term is the only important one and nothing else counts. However, if the exponential is going up, at some stage there might be some additional effects like competition between bees and things like that. You can understand why at the beginning these effects are not important. For instance, when the human species appeared on Earth, there were so very few groups that they didn't meet very often one another, and therefore the probability of killing one another would be very small. And in fact, it can be measured that not only in the prehistoric times, but even people which looked at the increase of population in the United States from its founding until now, they found this kind of behavior in which at the beginning you have some exponential increase, and only after that, after you have a certain density, you start feeling the corrections. And this is why I was a little bit resistant to people which ask me to explain this term, because this is not the important thing. The important thing, at least at the beginning of our analysis, was the fact that in situations in which naively, if you take the entire system as one single unit, you would naively think that it goes down. In fact, it doesn't, and it goes up, even though the parameters would tell you that it doesn't. So, but now I can now discuss the fact that there is this saturation. In fact, even the saturation is not really true. We'll see. Because this saturation is in the case in which you have the entire system just parameterized by one parameter. Consider the entire system as one thing. But if it is made out of many parts, some of the parts will go up and some of the parts go down, as we just described, by the A's going around. So what you get here is not at all what this equation is saying. And again, I remind you that it has a name, but you don't have to know why. People call it the logistic equation. Nobody really knows what. It's maybe because Verhulst, which introduced this term in Malthus' model, was a military man. So maybe he was thinking about logistics in the army. I don't know. But the point is that instead of this boring behavior here of just getting saturated, we are going to get a lot of fluctuations. And in fact, the fluctuations are very similar with what we learned in the first half of this course, in which you remember that because if you have big chunks of bees which are changing together, then you are getting fluctuations in the entire system in time, which are essentially described by some exponent, fractal exponents, which are equal with the exponent of what we call the Pareto law in that case, and it's essentially the law by which the islands themselves are now around A's are now distributed. And in fact, it turns out that the sizes of the islands of the crowds of the herds around which are formed are, in fact, if you make the statistics in a very wide range of parameters, they do fulfill this power laws of Pareto, and they do fulfill the relations which we have proved at the beginning of the course. In some other ranges of parameters, the situation becomes even more dramatic, and it looks not that much like the normal fluctuations of the stock market, but they look more like these economic cycles in which you really have big crises, because the islands become very, very big and very singular, and therefore when one island falls, it already has a very significant influence of the entire system. But this we'll see, probably not today anymore, but we'll see in the next lectures. In the meantime, I wanted to speak a little bit to give you some background on the logistic equation. As I explained, I don't really need it in order to develop the main stream of ideas which we are following now. But on the other hand, it's very difficult for me not to give you some information about the logistic equation, because it's a very well known. It's quoted in very many fields. So without knowing which field each of you are coming from, I know for sure that the equation is relevant there. So it was checked in very many things, from humans to bees and to microbes, and also in the diffusion of products, there is a model quite old by now. It's called the Bass model in the context of product market penetration. It's called the Rogers model in terms of diffusion of innovations. It essentially says, I forgot to transform this from a differential to the kind of form which we were discussing. But essentially it says that, forget this thing, that the change in x is proportional to two things. To what to the present value of x, which we already had, and also there is this square term, which is which is appearing from the following things. On one hand, the new people which are adopting a product, they are proportional with the people which already adopted, because they are exposed to that product through those ones which adopted. On the other hand, the number of people which are available to be contacted, if you think that there is a finite population which might be interested in that product, it's equal to the total number minus the number, the guys which already adopted. So essentially you have this linear term which we already discussed very many times, and you have this square term which essentially expresses what we said before, that after enough many people have already bought the product, there are not many people left for the product to be adopted by them. So there is this saturation. But essentially it's the same. I didn't make an effort to make it look exactly like our previous equations, but they are. These equations, they look a little bit more complicated, but because I do not depend on them, I will use them so you don't have to remember them for future applications. or for understanding future materials. It's just for teaching you how people in general are expressing their understanding about populations. This model was invented at the beginning of the 20th century by Sir Ronald Ross. He got the Nobel Prize for that. It's about malaria. Nowadays, we take as granted that the way malaria keeps being there is because there is this interaction between two populations, the populations of humans and the population of mosquitoes. If there would be only humans, then we would keep one another, isolated and things like that, and one would not get contaminated from one another. But there are the mosquitoes which can get infected from humans and then give it to other humans. So again, now we are taking this for granted, and it's well understood. But at the time of Ronald Ross, it was very new, and this is why he got the Nobel Prize. And Lotka, which came from the exact sciences, he took this model and he formulated it in a more and more mathematical way until, in fact, many other people adopted this model and started to make studies of it. So let me explain to you what these equations say. Again, I don't need it for future applications. I just want to spend 5 minutes in order to expose you first. Maybe this time it will not be successful, but maybe next time, years from now, somebody will try to explain something similar. So essentially, x1 is the number of humans, infected by the mosquitoes, and x2 is the number. The number of humans which infected by the malaria itself, and x2 is the number of mosquitoes infected by the malaria. And now the point is the following: humans. And this point here, it means that this is how much the number of humans is increasing in time. How much the number of infected humans is increasing, and this is how much or how the number of mosquitoes is increasing in time. The equation, by the way, I see that it doesn't take into account the death of humans and of mosquitoes, but apparently it was good enough for them to still get an evaluation of the it might be that these coefficients are already taking into account, as we did, we compressed in one coefficient a lambda minus mu both the birth and the death. It could be that these coefficients are taking into account also the death of the infected people. So you have the first term, which says the number of new people infected by malaria is proportional with the number of people which were already infected by malaria. They are contaminating one another. But they also can get contaminated from the mosquitoes. So it's proportional by another coefficient with the number of mosquitoes infected by malaria. But on the other hand, there are the number of people which can get contaminated is limited, because there's if already somebody was contaminated, the fact that the mosquito is an infected mosquito is stinging him again, of course, is not pleasant, but it's not giving him malaria anymore. So this is the nonlinear term which says this is the probability of already an infected guy, because x1, remember, is the number of infected humans. So the probability that the infected human is stinged by a mosquito, and this is already not by an infected mosquito, and this is already subtracted. It's plus, but A112 it's it's actually a negative number. So it subtracts from the number of humans which are infected times the coefficient of contamination plus the coefficient of contamination between mosquitoes and humans, it subtracts the probability that actually the mosquito is stinging somebody which is already infected by malaria. And the same thing it's for the mosquito. A mosquito which, these are the mosquitoes which are added to the number of mosquitoes which are infected by malaria. So they are proportional with how many humans they are meeting that they are infected, and the number of mosquitoes that they are infected and they can transmit to them, and but subtracting the probability that they are stinging some infected human, which however will not transmit to them the malaria because it's already there in their blood. So, so this kind of equations of the type that we wrote, in which you have some linear term, which in our case was, let's say, a lambda, or a lambda minus mu, and you have also nonlinear terms. This was introduced more than 100, not more. I think that Lotka wrote it in 1919, so it's almost 100 years. So these ideas were taken by Italian mathematician Volterra. He generalized this, but again you have this term in which the variation, the d of x, it means x at time t plus 1 minus x at t. And you have again that it's proportional to it, but also proportional with some nonlinear function, which is either competition, but it can be some other interaction. So he wrote it more generally. But in this particular case, it's a linear thing, so it's linear times x, so it's x squared essentially. It's very similar with the equation we mentioned. There is a very interesting book. Do we live in a Volterra world, in which it shows how many infinite number of applications to the real life are these Lotka-Volterra equations, as they are called. This was also used by a biologist, Hagen. He actually got the Nobel Prize, but for his experiments in very fast processes in biology. But after that, he actually studied a situation in which you had, in a sense, a situation very practical experiment similar to our abstractization, in the sense that he took only RNA chains and put them in a bath of proteins, and let them multiply. They weren't really live things because they weren't cells. They were just self-reproducing chains which were put in a bath of proteins. So they were multiplying, and they were having mutations. And then the question is, what is the relation between the speed of mutations and between the survival of the entire population? If they don't mutate at all, then the slightest change in the environment will make the dominant species unfit and will die. It's like in our case that the bees will not be able to move. Then the move of the A will collapse the entire thing. On the other hand, if the bees are moving too fast, then they will not be able to exploit by autocatalysis the presence of the A. If each bee which is created by the A goes away, then there is no way for them to multiply. So there is an optimal. This is what Hagen and Schuster have proved, that there is an optimal speed of mutations which allows an entire population to live. And maybe in terms of biology, this is just a nice thing to do. But if you think in terms of wealth, then it starts saying something about our society. If we are allowing the entire wealth to go only to the places where that is produced and not to diffuse to the others, then the slightest change in the conditions would make that guys useless, and their entire wealth useless for themselves and for the society. While if we do take care that the capital and the wealth is spread more uniformly, then we will have the entire society, including the richest one, being more insured against changes. On the other hand, of course, if one exaggerates and spread it completely uniform in places and in directions which are completely unproductive, then that is also not good. So there is some optimal way of wealth distribution which we might endeavor to find. How to enforce it after that, that's another issue. I'm finished.